are going to be about twisted bilayer graphene, and the first one is Louk Rademaker about charge transfer insulation in twisted bilayer graphene.
Well, thank you, and thank you for inviting me here. It's very nice. It's the first time in Brazil, so I'm having a very good time here. So I'm going to talk about a new system that probably in the future you'll hear a lot about, but because I guess this is probably one of the first talks you ever hear about twisted bilayer graphene, I'll just quickly review what graphene is, what bilayers of graphene are, before getting into what I think is the interesting or the important theoretical aspects of this material. Now, as you might remember, graphene is the stuff that you get if you take a pencil and a tape, and you put your tape on the pencil and you rip it off, and then you have graphene. Now, from a more condensed matter perspective, what's interesting about it is it has a single layer of carbon atoms where they form a honeycomb lattice. And the honeycomb lattice, as you know, has like these two inequivalent sides here, like blue and red. From now on, I'll call them A and B. And if you just look at the band structure on a honeycomb lattice like this, it has these interesting features that add what's called charge neutrality. So in the middle of the spectrum, there's these Dirac cones. So the dispersion there is effectively at low energy the same as Dirac equation, but without a mass. So it has this nice spin.k coupling. So that happens at 2 points in the Brillouin zone, at the k point, and the other point it's called the k prime point. They're related by rotation. Now that's single layer graphene, and it has a lot of interesting stuff, but the joke I once heard is that there's in the condensed matter community a carbon cycle. So they start with like zero-dimensional things like the buckyballs, and then one-dimensional things, the nanotubes, and then two-dimensional, the graphene. So now they're just starting stacking it up towards 3 dimensions. So the interesting then quickly went to bilayer graphene. Now if you just take 2 sheets of graphene and put them on top of each other, there's 2 simple ways that you can do that. The first is called AA stacking, where you put the carbon atoms literally on top of each other. Now in that case also in momentum space in the Brillouin zone, you have 2 Dirac cones on top of each other. But what happens is if you turn on the interlayer coupling, one of the Dirac cones is shifted down and the other Dirac cone is shifted upwards. So that's the effect of AA stacking. The other option is so-called AB stacking, where the A sides of one layer are on top of the B sides of the other layer. And in this case, something more interesting happens once you couple them. Of the 2 Dirac cones that you had, one of them gaps out, so you just open a gap. The other one is no longer linear, but becomes quadratic. So as you can see, it depends on how you stack, what kind of effective model you have at low energies. Now the twisted bilayer graphene is exactly as simple as you'd expect it. You just take two layers of graphene and you put them on top of each other with a slight angle. So what you then get is this beautiful Maré patterns. So you get a periodicity which is much larger than the original periodicity of your honeycomb lattice. And because you have such a very large periodicity in real space, what that means in momentum space is you get something which is called like a mini Brillouin zone. Your Brillouin zone folds back to something which is much smaller than the original Brillouin zone. And because of this angle, if you have a small angle between the 2 layers, what you get is that the k point in one layer and the k point in the other layer are no longer exactly on top of each other, they're slightly apart. So this would be the case if I just look at the band structure in the twisted bilayer without any coupling between the layers. But once you start introducing hopping between the layers, what naturally will happen is the point where these Dirac cones cross, they'll start, you start creating level repulsion between the 2. So you'll see that here. And now there's the amount of interlayer coupling, and the distance between the 2 depends on the angle. And there's already quite some years, about 10 years ago, some ideas that for certain angles you can actually tune the interlayer coupling and the distance between these points in such a way that the level repulsion is so strong that the effective Fermi velocity of the Dirac cones there vanishes. So these angles are called magic angles, and it was already theoretically a nice idea, because if you are at that point, at those angles where the Fermi velocity vanishes, yeah, okay, shoot. Yeah. Then magic happens like this. Okay, I should not step on this, I guess. Okay, so what you expect then is you'll get flat bands. And if you have flat bands, you know that interactions will dominate the physics. So you can get a lot of interesting interaction physics in a system as simple and clean as graphene. So that's what the group of Jorillo Herrero did in MIT. They published in March this year 2 papers in the same day. The first one, what they did is they created a series of these twisted bilayers at a certain angles, and they're getting very close to what theoretically was predicted to be a magic angle. In this case, what they then on top of that can do is they could gate the system, so they could control the actual carrier density, so they could sweep through these bands. So what you see here is the conductance as a function of the carrier density, and here at 0 is where these Dirac cones are. So you always see like a dip because it's become a semi-metal there. You have double degenerate bands, so what you have here is if you would remove 4 electrons per unit cell, and then you would have a band insulator. On the other side, you can add 4 electrons, and then you're here at these densities, and then you also have a band insulator. But just based on the band structure, what you expected if you're here, just the band structure should give you a metal, but it's clearly not. The conductance drops both if you add or if you remove 2 electrons, or if you add 2 electrons relative to charge neutrality, and that suggests if you have some kind of integer number of electrons in a band, yet it's insulating, that means that it's probably something to do with Mott physics. So that was their claim. So they say this is probably a Mott insulator of some kind. And of course the theory's question is then what it is. But before I get to the theory, let me just show you this is the temperature dependence of it. So at high temperature, which is on the left of this plot, it just behaves metallic, and then around 4 Kelvin it suddenly starts to drop both on the hole doped and the electron doped side around the same temperature, and it becomes insulating. So the 4 Kelvin scale is kind of important. Also, if they do the same thing in a magnetic field, they see that around 4 to 6 Tesla, depending on whether you're hole doped or electron doped, you also see that the insulating state is destroyed. So there's some kind of insulating state going on with a strength of approximately 4 Kelvin. So the next thing they did is actually to cool a little bit further. And that's where a beautiful surprise came in, that this is a color plot of the resistivity. So here you are at this this is the hole doped side, where you would have this Mott phase that starts at 4 Kelvin, which is slightly above here. But then if they cool down further, you actually see a state where it really becomes superconducting. So to make it more clear, here you see the red one is at half filling of this flat band. It turns up because it's kind of insulating, and then it drops down, it becomes superconducting at that point. So the superconductivity is not at a shockingly high temperature, 1.5 Kelvin, but the interesting thing is that this is the first time that superconductivity is seen in graphene, in just a system solely consisting of carbon atoms. And not only that, if you just look at the shape of this phase diagram, it must remind you of basically every other talk in this conference so far. So to summarize that, why is this so exciting? Well, it is a very clean system. Graphene is very well controllable. It has strong correlations, and that's something I guess everybody in this conference likes. But then, if you remember, this is a phase diagram for the cuprates, and this is like the phase diagram for the twisted bilayer graphene. It looks a lot the same. You have like a Mott phase in the middle, and if you dope it, you get some kind of interesting superconducting phase. Yes? Yeah, so the transition for the Mott phase is about 4 Kelvin, and the superconducting phase is about 1.5 Kelvin. Okay. So, yeah. So one thing that you can do indeed is look at how relatively strong is the superconducting phase. And one typical thing you can do is you can divide the superconducting temperature by the Fermi temperature, because now you have a very flat band. The Fermi temperature is not the usual 10,000 Kelvin that you're used to in other systems. So the twisted bilayer graphene superconductivity has the same TC over TF ratio as, for example, pnictides or high TC cuprates, or this, well, iron selenide is also a pnictide. So if you just look at the TC over TF ratio, it falls in this category of, I would say, unconventionally high superconductors, something you cannot get with simple BCS. So that means that we have now a system which we need to understand, and it can provide us new answers into the long discussion about what correlations mean for superconductivity and Mott physics and things like that. So this is, roughly speaking, what the world was suddenly, was suddenly announced in March at the last March meeting in Los Angeles. What what then the first theorist's question is what is the important effective model for this? So we know for the cuprates that it's either like the single band or the 3-band Hubbard model. So you need to dive a little bit into the details of this material to see what would be like the similar Hubbard model, but now for twisted bilayer graphene. In order to get there, I'd say that the most important question is what is actually the real space structure of the orbitals? Because you have these flat bands, but it depends how these flat bands are in real space, because the interactions that we are interested, they're all deriving for Coulomb interactions, and Coulomb interactions are something that depends on where the charges are in real space. So the rest of the talk, I will talk about what is the real space structure of the orbitals that are relevant close to this half filling of the flat bands where the supposed Mott insulating state is. Now there's one observation that's been already known for quite a long time when people also study twisted bilayers at larger angles, so far away from these magic angles, which is that if you make these twisted bilayers, there is part of the unit cell has effectively something that looks very close to AA stacking, part of it very close to AB stacking, and then by symmetry another part that looks very close to BA stacking, which is AB stacking, but then the other way around. And if you are at charge neutrality, the density of states, as a function of space, is highly peaked around these AA stacking centers. So that's this is a picture from the experimental paper where they say, well, this density of states is the largest at these peaks. So you imagine these peaks form a triangular lattice. So literally, the first idea is, oh, maybe this has something to do with triangular lattices, but it's probably a little more complicated than that. So what we did is we started looking at these bands a little bit more in detail. So rather than having this approximate picture of these cones and then these level repulsions, let's do it exactly. So what you can do is you can just take an angle, like a commensurate angle, so you get a very large unit cell, in our case with 11,000 carbon atoms in it, so you get 11,000 bands. You can just do a tight binding model where in plane I just do nearest neighbor hopping to get these Dirac cones, and then interlayer hopping, which exponentially decays with the distance. If you do that, you get, this is just a snapshot of a lot of these bands, but let's just zoom in close to this charge neutrality. What you see here is you see 4 bands. So around here they're almost degenerate, but what's important is the bandwidth is very small. It's about 11 milli-electron volt. Here you have 2 double degenerate states at the K point and equivalently at the K prime point. At the gamma and M point they look degenerate, but they're actually almost degenerate. They're like numerically not almost indistinguishable in what we did, but if you look at symmetries, they're actually not exactly degenerate. And then there's a band gap towards the remaining stuff down here. So the Mott insulating state would be when you half fill, let's say, this band here, the purple and the red one. So what we did is, well, now we have to solve this tight binding model so we can see how the charges are distributed once you start adding these, once you start occupying these orbitals. So the first thing we do is we look at the K point in momentum space, and then we look how it looks, how these states look in real space. So a little bit, what do we see here? This would be the unit cell. I hope you can see it, that this is these 11,000 atoms that I talked about. In the center, the way I draw it, the center is the AA type stacking, and on the corners you have AB and BA and AB, BA, etc. So the states at the K and the K prime points, what I show here is the size of the blobs is the absolute value of the wave function, and the color is the phase. So you can clearly see that these wave functions are not homogeneous throughout the unit cell. They are very strongly localized around these AA points. And these are just different, these are the 4 different states that you get. 2 of them are degenerate exactly at K point. So, however, of course, we're talking about half filling this band. So you should not only look at the K point, you should look at how this evolves if you go to the other side of the band. So let's look at the edge of that band, which is in this case at the gamma point. Now at the gamma point, I can make the same kind of plots where I plot the absolute value of the wave function in real space. And you see they vanish exactly at this AA centers. They form this ring-like structure. And a better way perhaps to visualize that is to plot the wave function as a distance from this AA centers. The orbitals at K are clearly peaked at the AA centers and then fall off, whereas the orbitals at gamma, they are vanishing at the AA centers and then grow and form this this bump at a finite distance. So because of this, our first thought was, well, there's no way that we can describe this band realistically with just one type of orbital, because if we want to describe the physics at this half filling, we need to have some kind of hybridization between an orbital that gives us these center-like orbitals at the K point and an orbital that gives us a ring-like orbital at the gamma point. So a simple effective model that we cooked up derives from that. So we could actually compute the overlap and how it changes when you go throughout the momentum space. So this is the amount of the overlap with center orbitals and the overlap with ring orbitals. So you see that if you start at K, it's 100% center, but the overlap drops. So there's at relatively small K, there's a sort of there's a switch from center to ring orbitals. What's important is that these center orbitals, if you look at their symmetry, they look like as if they live on a honeycomb lattice. And I think in the next talk, Oscar will talk more about the symmetries related to that. But for now, you just got to believe me, this is the way how you hop on a honeycomb lattice. These ring orbitals that we found, they actually hop more following a triangular lattice, because you can have both. If you have such a unit cell, you can have both honeycomb and triangular, and they actually mix. So in this case, you would give a Hamiltonian to describe 4 bands. 2 of them are ring, 2 of them are center-like orbitals, and you would here have a type of hybridization function that hybridizes to get this exact overlap. So if we take this Hamiltonian, the important take-home message here is that once we can fit it to the exact tight binding band structure, but we get this 4 bands, 2 ring, 2 center. The blue one, if you just look on the hole doped side, is mostly ring-like in real space here, but then when you go here, there's this hybridization and the repulsion between the two. So here they switch. Here it's the yellow or orange, whatever color that is, band that becomes more ring-like. So and the hybridization, the energy of the hybridization we found just in the fitting is 4.5 MeV. That's not something that is necessarily like hard, but like we said, this is like one of the first things that we thought about. But now that we have the real space structure, we can think about what the effect of interactions is. So that's Coulomb interactions, because everything, I mean, all the interactions we have all boil down in the end to Coulomb energy. So Coulomb interactions in graphene are actually very strong. That's not something that's usually much appreciated when people talk about single layer graphene, because it's so nice metallic. But there's a lot of research on what, for example, the on-site U is and the nearest neighbor repulsion in these carbon orbitals. And one simple way that you can parameterize that is that there's this would be the repulsion between carbon atomic orbitals in a graphene layer. And it's important to note that they actually don't really screen that well. It's just because of its semi-metallic nature, they're still pretty long range. Now, we took this form just from literature in the graphene, and then there's 2 physical effects that you can have. Now, the first one we have is discussed a lot, which is the Hubbard U. The way you compute Hubbard U is you take your orbital, what you're interested in, you square it, and then you just integrate over basically a product with itself with the Coulomb energy. Now, if you just do this, it gets a ridiculously high number. I mean, half an EV doesn't usually sound like a big number, but remember the bandwidth was about 11 MeV. So that seems like something you would immediately get localization, and it's an incredibly large value. So I have to say that I don't really believe this. And the reason that I don't believe this is because there's something else which you actually have to look at before you start to look at Hubbard U's, which is the unequal charge distribution. It's just a classical effect. Hubbard U is kind of a quantum effect, but this is just the classical effect of if you have just the classical charge distribution being uneven throughout your sample, that will cost a lot of Coulomb energy. So, and remember, if you just put in charges here, they will be strongly localized at the AA points relative to charge neutrality. So if you start filling this band, you will have an unequal charge distribution in the unit cell, and that will cost a lot of energy. So based on that observation, we started trying to quantify that. So if you just fill half fill this flat band just below charge neutrality, we can compute that you can actually get a very large interaction energy of 300 MeV. Now that is something that a lot of these bands have to pay, so this will affect all the bands. It's very difficult to do a self-consistent computation because you have these 11,000 bands, so we just start with like a 0th order, just an intuitive explanation of what we think should happen. Because if you have filled this flat band, you have filled basically only the center type orbitals because the hybridization only kicks in below that. However, what you also can do is you can take one of these charges, because you have 2 electrons per unit cell, take one of these charges and move it to these ring orbitals. In which case, we just suggest, let's take one localized electron in the ring, or hole in this case, one localized hole in the ring orbital and one localized hole in the center orbital. And the energy that we gain is actually 150 MeV, which is quite a large amount of energy. So pictorially, this looks like this. This would be the green would be more charged than average, red would be less charged than average, and if we switch, then the distribution becomes much more flatter. This is perhaps the best way of seeing that. Before you do this, what we call charge transfer from the center to the ring orbital, this would be where the charge is as a function of distance from the AA center of the unit cell. If you do this charge transfer, then the charge distribution is much flatter throughout the unit cell, and that gains a lot of energy.
So this should be captured by a Hartree-Fock calculator.
Yes.
Could you do that?
Yeah, we're planning on doing that, but Hartree-Fock with 11,000 bands is a bit, yeah, takes a while. So exactly, it's on my Outlook slide, literally the words Hartree-Fock. So. Yeah, so given this, but this is a kind of a first order approximation that you would have this charge, where we put the charges. Once you have the charges, once you say where the particles are localized, the next step when you do Mott physics is always, okay, what happens to the spins? So now there's an important thing to remember is that these ring and center orbitals were actually hybridized to some extent, which means that if they're hybridized, they can create an exchange. Just an antiferromagnetic standard Heisenberg exchange that you're used to, which is also mentioned several times during this conference, so I'm not going to explain that. The point is that this 4.5 or 4.7 MeV gives rise to this effective coupling, where now the J would be set by the, well, 2 times the square of this hybridization divided by the energy gain, or conversely, the energy cost that I have to pay to kill this charge transfer. Interestingly, that gives about 0.28 MeV. The state that this gives would be on every unit cell, you just have one electron in the ring, one in the center, and they form a singlet together. So it's a very trivial state. It's not some fancy spin liquid. It's not a magnetic state. It's just what's called a trivial paramagnetic Mott insulator. The energy scale that we got here is interestingly quite consistent with the energy scale that they see in experiments to destroy this state, either this 4 to 6 Tesla needed to destroy it with a magnetic field, and that's usually what you expect. If you have singlets forming with a 4, well, like a 4 Tesla bonding strength, then you can destroy that with a magnetic field of that strength, and the same thing for the thermal excitation of 4 Kelvin. Now, one of the reasons why it was exciting was, of course, the superconductivity. So I already mentioned that the idea was, okay, if you have a Mott insulator, just like in cuprates, and you dope it, you get a superconducting state. So how would that look like in this case? Well, just like cuprates, actually, if you remember well, cuprates are actually a copper-oxygen type of system, and depending on which direction you dope, you actually get the charges actually on a different place. If you electron dope, the charges are on the copper. If you hole dope, the charges will be on the oxygens. And in this case, I actually imagine something similar. So before including the interaction, below charge neutrality, I had this band where there was a mixed band of center-like and ring-like structure, orbitals. So if I include the repulsion that creates the localization, then you split into an upper and a lower Hubbard band. But now if you start from here and start to dope, it depends on whether you go up, like electron doping, or down, hole doping, to what kind of carriers you get. Specifically, start out from here and hole dope. That means that the charges you create are in these center-like orbitals. And if you remember, these center-like orbitals, they are hopping like they live on a honeycomb lattice. which means that the kind of superconductivity that you look at has to respect those symmetries. And here I just quote some literature that suggests that if you have charges on a honeycomb-like system, you get actually P plus IP type superconductivity. So this is not something we did ourselves. We just looked up in the literature what gives these charges on a honeycomb lattice. Similarly, you can do, starting from this half-filled Mott state, you can add charges, so electron doping. You get charges that live in these ring-like orbitals. These ring-like orbitals help like they're on a triangular lattice. So again, you just look through the literature, what gives a small amount of charges on a triangular lattice, and surprisingly, that gives a chiral D plus ID wave superconductor. So one of the suggestions that we make is if you're able to measure the symmetry of the order parameter in these twisted bilayer graphenes, if this is true what we're saying, you should be able to see a symmetry difference depending on whether you electron dope or hole dope relative to this half-filling state. Now I think I'm doing well on time, but let me just do the outlook. So as Thomas already said, what I've presented here is not very quantitative. So that's our next step that we're working on. And the first thing to do is, like I promised, Hartree-Fock to capture exactly how this charge transfer goes. Because this is, like I said, not really a quantum effect yet. It's something that should be able to be captured in a simple Hartree-Fock, though it's more complicated because of these thousands of bands that you need to take into account. Based on that, you get a new band structure. You get a better understanding of how the orbitals exactly look like in real space. And based on how those orbitals look, we can actually, yes, thanks. We can actually recompute the effective Hubbard U and then use like serious many-body techniques like, well, mean field or dynamical mean field theory or stuff like that to solve the effective model. So there's one part that I completely not mentioned in this talk, which is like the symmetry of these bands and just generic symmetry considerations and maybe the role of topology, which is something which the next talk will be about. So, yeah. So with that, I come to the end. As to summarize, we think that it's important to realize that these flat bands actually change orbital character when you go from the top to the bottom of this flat band. We call them ring and center orbitals around this AA stacking. And if you look at the interactions, we think that should lead to sort of a charge transfer between the center and the ring orbitals, which then naturally gives you a trivial paramagnetic Mott insulator state, with this nice prediction that the symmetry of the superconducting order parameter should depend on whether you electron or hole dope relative to this half-filling. So I did all this work together with Paula Mellado. And we have here our work on the archive if you want to read more details. And thank you for your attention.
Thank you very much. Are there questions? Yes.
Like most of us, we like to think about set of orbital to start with, right? Mm-hmm. But now I look at your result. At K point, you have this centered orbital. Yeah. But all four bands had a similar center orbital with a different phases, right? But the distributions are similar. Yeah. And if you look at the gamma point, you see that all four are ring-like, right? Yeah. So if I now mentally try to construct a Wannier function, which is what everybody should have been doing, then I can tell you that you're going to have orbital that are very delocalized, meaning that it cannot be just well confined within this hexagon you have, because you need to be able to cancel the Wannier function, the orbital at a momentum. At certain momentum, you need to cancel the center or the tail. So the Wannier function must be way bigger than this single hexagon. Otherwise, this will never happen. Okay, so what I'm saying is that if this is the case, then in order to build, assuming that these four bands are complete, and we don't allow them to relax and so on, this Tybanian Hamiltonian must be composed of orbitals that are much bigger than this hexagon. Has anybody done that? I don't think that's what you have. And this idea that you have 2 ring plus 2 center made no sense. Absolutely made no sense. We can talk about this a little bit in private. Well, because you need to cancel them to the point that all 4 look like a ring at the K point. Sorry, at the gamma point. That cannot happen if you have 2 center, 2 ring.
Well, yeah, but...
Right? Okay, that will never happen.
So there's two ways if you have such a difference in real space structure of a band. So this is before talking about the orbitals. If you have such a difference in how this structure looks like, there's two things you can do. There's what you suggest, which actually Oscar is going to talk about, which is indeed one-year functions that are larger than your unit cell, in which you can create difference between k and gamma points by having like cancellations between different phases and stuff like that. That's one way of going about it. The other way is that you can say, well, there's actually two orbitals which are hybridized, in which case we just literally wrote down a model that does that has exactly these spatial structures as you can see them in the real space tight binding model.
But are they orthonormal?
Yeah, of course they're orthonormal.
If they're orthonormal, that's what we call one-year function. You cannot escape from this issue that I just mentioned. No matter how you do it.
I don't understand. I mean, these colored guys, this is within one unit cell, just a wave function, right?
You want to pretend there are two of this and two of that, right?
Yeah, but all these, look,
right.
I
now
have
go to a particular momentum space.
Wait a second. Let me go back to the, okay. So here's the K ones. These four guys are orthogonal. So then these guys, how they look like at the gamma point, are not exactly orthogonal. However, what we can do is we can take these guys, now I have 8 orbitals, I can just Gram-Schmidt orthogonalize them, in which case I have 8 orthogonal wave functions within the unit cell, and then I can just project the Hamiltonian, like this 11,000 band Hamiltonian, onto those 8 bands, and I get this thing that I had in the next slide.
So you use an over-complete basis.
No, I'm not using an over-complete
basis. There are only 4 bands, and you're using 8 orbitals to describe them.
There are 4 bands.
And you're using 8 orbitals.
Flat bands, but I'm saying that there's these bands which are lower there. There's 11,000 bands. So what you need to reduce it to a sort of minimal number. You can say maybe that minimal number is 2, because we don't care about the Dirac cone. We don't care about, that's actually the minimal model. But then you say, oh, maybe we care about the Dirac cone. So we double it to 4. And I'm saying, well, these bands have a mixed orbital character. So what you need to do is you need to include these guys that are on the other side of the band insulating gap, right? Just like in a topological insulator, you have a gap, and the bands on both sides are both of mixed orbital character. That's not an uncommon thing in materials. So what we're saying is we're including these bands below this band insulator gap, some of them, not all 11,000 of them, but some of them. And in that case, what you do is you create effective bands that are mixed orbital types, as to create the difference between the center and ring like real space structure. What you're saying is also a possibility, and I think, Oscar, you will get more into that. No, but like I said, we're still it's a very young field.
Let's discuss in private.
Yeah.
Yes. Okay, thank you. Are there more questions? Maybe I have just a fast one. If you can go 2 slides back, because you had twice G plus ID. One more? At the end, completely at the end, 2 back. Further.
Oh, yeah, sorry. Yeah,
it's P plus IP, right?
Oh, thanks.